In the ancient world, men of science, cataloging the visible universe, observed a star of greater brightness than the first magnitude and named it Saturn. Later, in the first decade of the space age, men of science again applied the name Saturn to a giant rocket vehicle, an instrument of far greater magnitude than its predecessors, created for the peaceful invasion of space. This Saturn promises to enrich the experience and knowledge of man far beyond existing limits. The discovery of Saturn the planet and the birth of Saturn the space transport are separated by a span of 3,000 years. Yet only a little more than 3 years elapsed between the decision to produce the Saturn rocket and its preparation here for flight. This accomplishment, some of a series of achievements, the steps to Saturn, is in itself an historic chapter in the evolution of rocketry, key to the conquest of space. The origins of rocketry are buried deep in history. Yet there is a point at which the rocket principle became a practical consideration as the means of investigating matters beyond Earth. In 1926, Dr. Robert H. Goddard, an American college professor, successfully demonstrated the fundamentals of controlled rocket flight. His theories, still valid, shaped first outlines of a now dynamic and vital area of science, rocket technology. Dr. Goddard, the practical visionary, thus took the first steps to Saturn. Yet in the wake of World War II, United States developmental efforts were largely directed at producing military rockets. In 1953, the United States fired its first crew ballistic missile, the Redstone. Redstone contributed heavily to the technical capability of the infant American rocket industry. Thus, later, the intermediate-range ballistic missiles and the larger intercontinental missiles could dwarf the performance figures of earlier rockets. Dr. Goddard measured his successes in linear feet. Jupiter, an IRBM, could precisely target an objective 1,500 miles distant. Jupiter flew first in 1957. And in that year, Sputnik 1 was placed in orbit. With that single act of rocketry, the character of international endeavor was abruptly altered. Scientific achievement for the first time became a popular barometer of national reputation. And the area of ambition shifted from the tiny confines of Earth outward to the measureless arena of space. This, too, was a step to Saturn. It made mandatory the immediate utilization of military rocket systems as space taxis. In January of 1958, a Jupiter C vehicle hurled into orbit the first U.S. satellite, Explorer 1. An impressive achievement score was rung up by many subsequent space probes. But these steps to Saturn, taken together, paid a far more important dividend. They advanced the whole new technology of space rocketry. They enlisted and trained a Space Corps cadre, technicians, engineers, planners, researchers, theoreticians. All were permitted to learn, sometimes to bitter failure. But the technical establishment grew, matured. And so the Saturn project, able to build on proven experience and capability, became a practical enterprise. In August of 1958, the Advanced Research Projects Agency gave the go-ahead on Saturn development to the Army Ballistic Missile Agency. Saturn was later transferred to the National Aeronautics and Space Administration upon creation of the Space Agency. Development as a priority NASA project continues at the George C. Marshall Space Flight Center Huntsville, Alabama. Defined, Saturn is a rocket vehicle system of great flexibility designed to serve over an extended period as the multi-purpose workhorse of peaceful space exploration. Prime objective, to contribute to the priority national space goal, manned lunar landings. Yet the space payoff, the mission, can only be as rich as the basic capability of the carrier rocket. So working toward the moon began with the development problems of lifting great bulk and weight free of the Earth. The requirement, a booster of enormous brute force to muscle upper payload carrying stages into near space. So a significant step to Saturn was the executive decision, develop quickly the big booster, use available, reliable hardware, create a flyable first stage, producing thrust in the order of 1.5 million pounds. This power output was almost 4 times the power of any rocket propulsion system in this country. Indicated was a task involving clustering proven engines, tankage, feed systems, and associated hardware, all combined in totally unprecedented multiples. First, the basic engine. Chosen was an improved and uprated unit of high reliability, seasoned in the IRBM and ICBM programs. The H-1, a liquid propellant engine using RP-1 fuel and liquid oxygen, could produce 188,000 pounds of thrust. Multiplied by 8, it would, when successfully clustered, give U.S. space ambitions the big lift. Engine development was rapid. First full power firing at the Santa Susana test site in California took place only 3 months after the go-ahead date. And 4 months later, the first engine reached Alabama. To the basic engine, many engineering refinements had been applied. These worked toward functional simplification, which greatly increased reliability and efficiency. Repositioning of key components improved the overall unit configuration, reduced weight, and allowed easier boat tail maintenance. The 8 engines are set in 2 square patterns. Inner engines are rigidly mounted and canted slightly to concentrate thrust vectors close to center of gravity. In the outer pattern, engines are canted outward to a greater degree and can be gimbaled. Gimbaling, or swiveling, is the means of directional control of the vehicle. For by command signals from the guidance computer, the engine, gimbaling, can alter the direction of its thrust, and thus the direction of the entire rocket. Maintaining the clustering concept, booster tankage, which forms the basic thrust-carrying structure, could also be utilized in multiples. Tooling for tankage in Redstone and Jupiter diameters was readily available. Thus, development time to prove out tank configurations was reduced sharply by using existing facilities and experience. Booster superstructure, then, was designed to comprise 9 propellant tanks. Center tank of Jupiter diameter and 4 Redstone diameter outer tanks carry liquid oxygen. Fuel is carried in the 4 remaining outer tanks. A thrust frame assembly links together all tanks and supports. The booster tanks carry a total of 750,000 pounds of propellant, which through a manifolding system can be gulped dry by the engines in less than 2 minutes. The manifolds delivering the propellant have an interchange capability so that any tank can feed any engine, and propellant levels in all tanks are maintained equal during depletion. At the top end of the booster, 48 fiberglass spheres store the gaseous nitrogen used to pressurize fuel tanks. This, during operation, helps to maintain uniform propellant flow. Liquid oxygen tanks are pressurized by gaseous oxygen tapped from engine heat exchangers. Fabrication of the booster goes forward. But before this, every component, every piece of hardware of any size or function must prove itself by actual operational test. Testing qualifies the component's performance. Probes for hidden, unsuspected flaws. By endless repetition determines the reliability, and sometimes fixes the precise limit of life, the breaking point. The test program, proving point of the development cycle, puts the stamp of acceptance or rejection on every item. There are no unimportant items. Final assembly complete, the booster is ready for functional testing. Captive within the test tower, the engines will be fired as a cluster unit for the first time. Now the specters of rocket propulsion, the intangible, the unpredictable, combustion instability, structural weaknesses, excessive vibration, sonic stress, all rise to haunt the test engineer. At ignition, everything is committed. From the first, performance met all expectations. On April 29, 1960, all 8 engines firing as a unit according to plan for the first time produced more than 1 million pounds of thrust. While the booster emerged as the major accomplishment, other steps to Saturn, thousands of them, were being taken each development day. Hundreds of industrial contractors contributed greatly diversified skills and products to nourish the growth process of the overall vehicle. Throughout the nation, personnel, services, material, all the know-how of highly specialized firms and agencies were integrated uniquely into this single space venture. At Marshall, management teams wrestled with the intricate combinations of time, capability, and funding. And a first citizen, looking toward the problems of space, noted carefully the details of the complex mosaic of the total Saturn plan. And in the laboratories of the Space Center, the routine assault on detail, the minute attention to the tiny hardware organisms of a great rocket continue, quietly, persistently. Study the little-known destructive vaporization of material and tissue in a space regime. And with space captured in a bottle, discover an effective lubricant for moving parts functioning in a total vacuum. Endlessly examine the environmental deterioration of matter, especially metal. Search for answers to the questions of space existence. Search, in fact, for the questions. And in the meantime, new facilities must be developed to meet the accelerated needs of the program. And it is axiomatic that facilities pace all other effort. Facilities for fabrication, engineering personnel, for development, for testing, and inevitably, for launch and flight. For Saturn, there was Launch Complex 34. 2 years in the making, dominating the north end of the Cape with its towering 300-foot gantry, Complex 34 awaited Saturn. From Alabama to Cape Canaveral is 2,000 miles by water. Too huge for conventional transport, the Saturn vehicle floated the first leg of the journey to space on the back of a barge. In a summer dawn, Saturn appears off the Florida coast. The piggyback passenger, prone and piecemeal, is tugged a final short step toward the launch site, toward fulfillment. The inland river routes to Canaveral are lined with throngs. the young, the curious, all those who sense in the arrival of the recumbent giant the meaningful appointment with history. And some waiting who know intimately the history of the appointment. Assembly into flight position begins. First, the booster, now vertical, in flight position on the launch pedestal. For the first research and development flights of Saturn, the two upper stages are not powered. The second stage here is merely a water-filled passenger, an aerodynamic component. In later versions, this Saturn stage will be powered by high-energy liquid hydrogen, liquid oxygen engines. The third stage, a modified Centaur, is also inert here, programmed to ride with water ballast. This stage may also be powered in later Saturns by two similar high-energy engines. To complete the vehicle, the nose cone is mated to the upper stage. This, the first Saturn, does not carry an active payload. But later, when the giant has matured, the installation of the nose cone, filled with instruments and detection and recording devices, or communication systems, will be of overriding importance. And in time, the descendants of Saturn will be topped by a spacecraft bearing humans en route to the moon. Saturn is ready for flight. "3 years plus a few months, and now only a few hours away from the absolute test. Countdown was initiated at 11 p.m. October 26th. After daylight, the gantry moved back on schedule. Saturn stood alone. Shortly after 9 a.m., a short hold occurred to wait out a weather condition. Weather okay, countdown resumed. 10:05 a.m., October 27th.
Minus 1 minute. 34, 35, 36, 38, 50, 40 psi on lock tanks. 41, 42 is fast. 42 and a half, 43, 8 kc operator. 45, lock tank pressurized. Jumping 3 seconds. Okay, power transfer complete. Top plug disconnected. 20 seconds. Right on.
16 stories tall, weighing nearly 500 tons, Saturn flew. All objectives were achieved, all satisfactorily. But beyond the moment of great accomplishment, the engineering and scientific triumph, what does the first Saturn flight bring in return? Earlier, this was said.
space is open to us now, and our eagerness to share its meaning is not governed by the efforts of others. We go into space because whatever mankind must undertake, free men must fully share. I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space, and none will be so difficult or expensive to accomplish.
Thus, toward that goal, a giant step, the first Saturn, a product of directed human talent and energy, which will be followed by other steps, to eventually give to all mankind a freedom from the restraints of Earth, to probe toward the enlargement of knowledge, to move toward the far reaches of the unknown, to bring the visible and invisible universe into the catalog of human experience. These steps to Saturn continue.